All right, welcome. Today, we're cracking open a mathematical toolbox that, believe it or not, engineers, physicists, and even game designers use every single day. We're talking about vector algebra. And trust me, it's so much more than just a bunch of arrows on a page. It's literally the language we use to understand and build the 3D world all around us.
So it really begs the question, right? How can a simple little arrow on a piece of paper solve these massive complex problems in geometry and physics? Well, that's exactly what we're going to dig into. You're about to see that these aren't just any old arrows. They're incredibly powerful tools that play by some very specific rules.
Okay, so let's jump right in and grab our very first tool from the toolbox. But before we can really use a vector, we've got to have a super clear, rock-solid definition of what it is. And I say that because there's a really common mistake people make that we need to clear up from the get-go.
Now check this out. Most of us remember from school that vectors have two things: magnitude, their size or length, and direction. But look at that third condition. This is the one almost everyone forgets, and it is absolutely crucial. A quantity has to obey the laws of vector algebra. If it doesn't follow those rules, then guess what? It's not a vector. Simple as that.
To make this a little more real, just think about some stuff you probably already know from physics class. You've got velocity. That's not just how fast you're going, it's how fast you're going that way. Then there's acceleration, which is a change in that velocity. And displacement? That's just how far you've moved from where you started and in what direction. All of these guys play by the vector rules.
And this is the perfect example to drive the point home. Take electric current. I mean, it's got a magnitude, right? Like 5 amps. And it's definitely got a direction. It's flowing through a wire. But, and this is the big but, if two wires meet at a junction, the currents just add up like plain old numbers. They don't follow vector addition laws. So it fails that all-important third test. It has direction, but it's not a vector. It's a scalar.
All right, let's grab our second tool and see where this takes us. This one is called the dot product. And really, all it does is help us answer a very simple question. How much do these two vectors line up? You can think of it as our alignment tool.
So, here's the most important thing to get about the dot product. When you dot two vectors, you don't get another vector back. Nope. You get one single number, a scalar. That's actually why it's also called the scalar product. And that one little number, it tells you a whole story about the angle between those two vectors.
And here's how you read that story. If the number you get is positive, it means the vectors are generally pointing in the same direction. The angle between them is acute, less than 90 degrees. And the bigger that positive number is, the more perfectly they're aligned.
Now, what if the dot product is exactly 0? This is a huge deal. It's a massive signpost. It means the two vectors are perfectly perpendicular to each other, at a perfect 90-degree angle. Seriously, this is one of the most useful tricks in the entire vector toolbox.
And you guessed it, if the dot product comes out negative, it means the vectors are generally pointing away from each other. The angle between them is obtuse, more than 90 degrees. So you see? Positive, 0, or negative. Each result gives you an instant, powerful insight into how these two vectors are arranged in space.
Okay, tool number 3. This one's called the cross product, and it answers a completely different kind of question. If the dot product was all about how much do you align, the cross product is all about which way is up. It helps us find the one single direction that is perpendicular to two other vectors.
And here's the big twist. Remember how the dot product gave us just a number, a scalar? Well, the cross product gives you a whole new vector. That's why people also call it the vector product. And the most important thing about this new vector is the direction it's pointing.
This is what makes the cross product a 3D powerhouse. Imagine you have two vectors lying flat on a table. Together they define that flat surface, right? Well, their cross product is a new vector that points straight up, perpendicular to the tabletop. It instantly generates a third dimension for you. It's an incredible tool.
Okay, so let's recap. We have a tool for alignment, that's the dot product, and we have a tool for orientation, the cross product. So now, let's see what happens when we make them work together. We can answer some really classic geometry questions, like how a bunch of vectors relate to each other.
So here's the puzzle. Imagine I give you 3 random vectors. We'll call them A, B, and C. How can you figure out if they're coplanar? That's just a fancy word for asking if they could all lie flat on the same surface, like a tabletop. It sounds like it could be a really tricky problem, but with the tools we have, the solution is surprisingly easy.
Just look at how beautifully these two tools work together. Okay, step 1, you take the cross product of vectors B and C. What do we know about that?
It gives us a new vector that's perpendicular to the little plane that B and C are sitting on. Okay, step 2. Now you take the dot product of our third vector, A, with that new perpendicular vector. Well, think about it. If A is also lying flat in that same plane, then it has to be at a 90-degree angle to our new vector. And what happens when two vectors are at 90 degrees? Their dot product is 0. It's an absolutely perfect test.
So, we've got our tools, we know how they work, now for the payoff. Let's see how all this abstract stuff gives us these incredibly simple, elegant solutions to real geometry problems. Problems that would be a whole lot messier to solve any other way.
I mean, this is just so cool. You need the area of a parallelogram made by two vectors? No problem. Just find the magnitude, the length of their cross product. Done. What about a triangle? It's just half of that same number. And like we just saw, you want to know if three vectors lie on the same plane? Just check if that scalar triple product is 0. These are just insanely efficient shortcuts.
Hey, here's a little pro tip for you, a really clever trick that connects our two biggest tools, the dot and cross product. It's called Lagrange's identity. It basically says that the squared magnitude of the cross product plus the square of the dot product equals the product of their squared magnitudes. It's a bit of a mouthful, but it's a fantastic shortcut if you already know a couple of these values and need to find another one fast. So it's pretty clear that vectors give us this amazing, elegant language to describe the 3D world we live in. But that leaves us with one last, really mind-bending question. Everything we've talked about today, it's the foundation for a much bigger idea called linear algebra. And that's a field that lets mathematicians and physicists work not just in 3 dimensions, but in 4, 5, even 11 dimensions or more. So what happens to geometry when you get to a place that you can't even picture in your mind? Well, that's where the real adventure begins.